what I'm going to need you to do with me is draw two cyclists, okay? One of them is going to be a cyclist that's not leaning over. So I'm going to draw it like this. I'm just going to draw it a little bit thick because I'm going to have stuff on here in a second. So this is a cyclist, and they are on a flat surface. Okay. So let's analyze the forces that are happening here. And just as a little point, this is going to be a lot easier if we consider this from the cyclist's frame of reference, okay? Now, I know that's not inertial. They're actually accelerating because they are turning, of course. But the forces that we'll be able to consider are much more easy to see if you think about it from the cyclist's point of view. Okay, so over here, I already considered some forces, right? How many of them are still relevant here? How many are still relevant?
All of them.
All three, right? Let's have a look at them. Let's start with, say, the gravity force, okay? Now, the gravity force, the weight force, I should say, is here. Now, what's lovely about this, I'm actually going to consider the forces acting at different points along the actual dimensions of my cyclist and bike, okay? So here's, oops, sorry, that's not right. mg is actually acting on the center of mass, right? This is what we were discussing before, of like, you know, trying to pick a point for where should we consider our forces. Okay, so the center of mass is going to be somewhere around here. So there's mg. That's good. Okay. What other vertical forces do we have here? The normal, because the ground is still flat, right? So from here up that way, I've got the normal force. Now, looking at these 2 points, okay, are either of them fixed? Are either of them the points about which rotation would happen if it were to happen? Look carefully. I'm trying to think, is there an O, right? Now, I think it is the point of contact back here on the ground, the point we picked earlier, okay? If we are going to incline, if we're going to rotate, just like that cyclist over there, we're going to incline like this, right? This point's going to stay put, the tire is going to stay on the ground, and the rest of our body is what tilts back and forth. So this is kind of like our fixed point here. Okay, now we imagined our turn going to that side of the board. So there is a friction force, isn't there? There's a lateral force. So let's draw it going off here. There's our lateral force. Now that was all fine. This was in an inertial frame of reference. Over here, there is one force we haven't accounted for. If you're thinking about the cyclist's point of view, what force is it? Okay, I'm thinking about it from, what's changed is not whether I'm thinking about how big it is in terms of like this is still, it's still only one dimensional, so it's actually not going to experience any area. It doesn't take up any area, okay? What I'm thinking about is if I'm the cyclist and I'm turning, right? Think about those, think about the wall of death guys, right? What they are experiencing is a fictitious force away from the center of the turn. Does that make sense? They're experiencing, I'm going to call it C for centrifugal force. It's fictitious, right? But in the frame of reference, it is, they can feel that sensation, okay? All right, so I've got all of these forces now in my non-leaning cyclist. Maybe I'll write that up the top. Non-leaning cyclist.
Wait, so is the cyclist turning to the right or the left?
Yep, cyclist is turning that way, which is why the friction force is going that way laterally.
But the centrifugal.
Yeah, the centrifugal force, not centripetal force goes to the center. Okay. Centripetal force, and centrifugal force is going away from the center, and it's fictitious.
So, if the lateral force is the friction force,
yep,
then shouldn't it oppose the centripetal force? So it should be the other way.
The lateral force is the centripetal force.
Yes, that's right. It's because you're turning your wheel. You're turning your wheel. So it's the traction of the wheels which has friction, which actually makes you negotiate the turn. So the friction is actually, does that make sense?
Yeah.
So Tom nailed it. Okay, now have a look for a second. Just like with our whiteboard markers before, I'm going to ask you 2 questions. First, I want to talk about the linear forces. What is the net linear force? Net linear force is 0, right? You can see balanced, 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 balanced. All good, okay? But now that I have this category of torque in mind, now I want to think about 1, 2, 3, 4 forces, and I want to think about the torque force that is exerted, okay? Let's start from the ground, okay? These guys here, how much torque do they exert?
Wait, what?
The lateral force and the normal. How much torque do they exert? And the answer is they don't exert any because they are at the point of rotation. They are like putting a force, no matter which way I don't care which way you're facing. If you're pointing at the actual point of rotation, you're not going to make this whole thing spin around at all. Okay? So these guys, they contribute no torque. So far, so good. What about this one? What about the weight force? What torque does it exert?
Zero.
Answer still nothing, right? Because you can only tilt this way or that way, and this force is going down, right down through toward the point of rotation. So it doesn't exert torque either. There's only one force that exerts torque, and it's this guy, right? This guy over here. So it is going in what direction? It's going this way, so I guess I would call that anti-clockwise, right? Anti-clockwise. Is there anything to balance this torque? Nope. So the cyclist falls over, okay? If they are turning their wheel and not leaning, they're going to fall. And paradoxically, they're going to fall out of the turn. They're going to fall out of the turn, okay? So this is the non-leaning cyclist, and it is not, whoops, I'm going to stay with this, it is not a stable situation. So now let's draw our leaning cyclist and see what changes. Okay? We're still going to have the ground, which is flat. But now, we're going to have to draw our cyclist off at an angle into the turn. Okay, so I'm going to draw them off like so. Got my cyclist. Now I'm going to put my forces on one at a time. Again, going to start from the ground. Okay, these forces here, the lateral force and the normal force. What's changed in terms of where they're facing and how much torque that they exert? What's changed? Nothing has changed. Nothing has changed. Right here, right, the lateral force is still going the same way in the same amount, and the normal force is still perpendicular to the ground, and they're still at the point of rotation, so not exerting any torque. Okay. What about these two guys over here, right? Up at the center of gravity, which way is the centrifugal force going? It's still going towards the outside of the turn. It's still going this way. Right? It's still exerting a torque in the anti-clockwise direction, so maybe I'll just add that in now. So this is the fictitious force. Yeah. But here is the money moment, right? The last force that we have here is the weight force, right? Now what's happened to the weight force? Well, it's still vertical, right? But what's it directed at now?
Next to the board.
Yeah, it's not directed at the point of rotation anymore. It's directed away from that, right? So this is mg, right? But with respect to the cyclist, it is imparting this, where's the way I'm going to do it? I'll do it this way. It's imparting a clockwise torque on the cyclist, which balances out with the centrifugal force, that anti-clockwise torque that's happening there, and that's why this is stable. That is why not just the cyclist can, but the cyclist must actually lean over to not fall over, okay? Which is kind of weird and counterintuitive, but also super awesome. I think that's really cool to understand. Okay?